Hey guys, all right, so we're going to talk a little bit about electron configuration in this video. Now that we know from the last video the shapes of the orbitals and their orientations, which all that, of course, comes from quantum mechanics, right? Now we can talk about are electrons in any of those orbitals, and how do we know that, okay? And so that's what this is. That's what electron configuration means. What orbitals are your electrons in? So the first thing to know about all this is something called Pauli's exclusion principle. And it basically tells you that you can't have two electrons in the same place, okay? So another way of saying that is every electron inside the atom has its own unique set of quantum numbers. This is like its unique address. And you can't have two electrons living in the same address, in the same place, okay? They each have to occupy a different area of space, right? And that where that area of space is maybe a little bit, counterintuitive to define because it's like this probability map, but it's defined by the quantum numbers, okay? And so take, for example, the three sets of quantum numbers for the three electrons in the element lithium. A neutral lithium atom, right, has three protons, three electrons. So there's going to be three types of quantum numbers. And if you look at these, two of them are going to have n equals 1, principal quantum number. One of them is going to have n equals 2. They're all, it turns out, going to have L equals 0. And they're all going to have m sub L equals 0. And so if you look at these first two, those are actually the same. And quantum mechanics tells us that that can't happen. And so for that reason, we have to actually introduce, and quantum mechanics will do this naturally through the math, okay? This comes out of the math. A fourth quantum number, which is m sub s, okay? This is the magnetic spin. This is the electron spin or magnetic spin. It's called the spin of an electron. And this can either be plus 1/2 or minus 1/2. No matter what the other quantum numbers are, you can only have plus 1/2 or minus 1/2 for this quantum number m sub s, okay? And so now the Pauli exclusion principle is satisfied because electrons 1 and 2 have not the exact same set of quantum numbers. At least their m sub s's are different, okay? And so now what we're going to do for atoms that have more than one electron, multi-electron atoms, we're going to figure out where these electrons go. And there's basically an energy ordering of the different orbitals, and that tells you how to put the electrons in there. You're going to build up, okay? You're going to put your first electrons in the lowest energy orbitals. Those are generally going to be your s orbitals, okay? So for any n value, your ns generally is going to be less than your np, your nd, your nf, your ng. We didn't talk about that. G orbitals are above f orbitals. Don't worry about g's, okay? So your 3s energy is going to be filled before because it has lower energy than your 3p, than your 3d. Generally, that will be true, okay? Why didn't I write 3f orbital here? Why didn't I write 3f orbital? Let's think about that. So that would have been a breakout session type problem for us. But for now, let's go to our whiteboard and let's try to figure that out together, okay? So here we are on the whiteboard, and what we're going to do, why is there no 3f? So let's try 3f. That's the question we're asking. Why is there no 3f orbital? I'm telling you that there's no 3f orbital. Okay? No 3f orbital. Why? Okay. Well, what does that mean? If we have a 3f, the 3 tells us that n equals 3. What does the f tell us? The f tells us, if you remember from the chart in the last video, the f tells us that L equals 3. Well, from our quantum mechanical rules, recall that if you have an n equals 3, L can only range The L range is from 0 integers to n minus 1, okay? Well, n minus 1 is 2, right? Because n equals 3. And we're wanting L to equals 3. So that's why L cannot equal 3. L can only be 0, 1, or 2. So you can only have 3s, 3p, 3d, that'd be 2, okay? But you can't have 3f orbitals because of that, all right? So that explains that. Let's go back to the slides now. Okay, so that explains that. A little bit aside. Okay, review question. What are the allowed quantum numbers for the following orbitals? So similar type of stuff that we just did on the whiteboard here. Let me do that on here. Okay, so this is a dumbbell type shape, right? So the dumbbell, we know we're gonna have a P. It's a P type orbital. And we have one radial node. We know that the smallest p orbital that is allowed is a 2p, okay? If you go through the quantum numbers, that's 2p is the smallest one because n equals 1 is the first time that you can make a p, right? Because L can only be, sorry. N equals 2 is the first time that you can make a p because L in that case can only be 0 or 1, right? So that's the first time you can make a P. All right, so, but now we have an extra node here. We have 2 nodes, right? We have kind of the default node, but we also have a radial node. There's a default planar node that makes it a dumbbell. This is the radial node. So it's gonna be 1 higher than the lowest one we can make because we have a radial node. So that's gonna be a 3P. Okay, what about this one? This one is an S, it's looking like a sphere. And again, there's 1 node there that it's showing you, 1 radial node. So the smallest S orbital you can make is a 1s, right? And so this is 1 higher because there's 1 radial node. So this is gonna be a 2s. Look at the previous video if you're confused about this with respect to nodes, okay? And this one doesn't have any sort of nodes that are these sort of radial nodes, right? So this is basically the smallest d orbital. This is a d-type orbital, and the smallest d orbital is 3d. So we're going to talk about the quantum numbers for these. Allowed quantum numbers would be for the 3p, n equals 3. A p is L equals 1, and that can have m sub L of -1, 0, and +1. It could have m sub S is always, the allowed quantum numbers are always +1/2 and -1/2. Okay. For the 2s here, your allowed quantum numbers, well, it's a 2s. It's going to be n equals 2. It's an s. So L equals 0. And recall that m sub L can only go from negative L to positive L. So that's negative 0 to 0. So it's going to be 0. And again, for m sub S, that's always -1/2 spin down, we call that, or spin up, we call +1/2. Okay, and then for 3D, well, n equals 3. D, by definition, a D is L equals 2. Okay, and then our MLs for that, M sub Ls can go from -2 to +2. So we can have -2, -1, 0, +1, +2. And then our M sub S, again, is spin up or spin down, or how I'm writing it, spin down, -1/2, and spin up. Okay? So that's basically it for this type of problem. All right, see you in the next video, guys.